कल हमने देखा कि आपके पास अगर कोई पावर सीरीज है, इफ यू हैव अ पावर सीरीज, तो इट इज कन्वर्जेंट और इसका रेडियस ऑफ कन्वर्जेंस अगर आपके पास पॉजिटिव है, तो द फंक्शन दैट दिस पावर सीरीज रिप्रेजेंट्स becomes an analytic function. Is analytic on this disk of convergence. And not only this, we also saw that all the derivatives of this function exist. Every derivative of this function exists, and indeed the formula for the derivative of this function can be obtained by differentiating this series term by n factorial n minus k factorial a n z to power n minus k. Let me demonstrate the use of this thing here. Let us take a well-known power series, and this is the geometric power series, and we know that its radius of convergence is 1. This radius of convergence is 1, and its sum is equal to this function. We know this thing. So here this function is analytic. Obviously 1 upon 1 minus z is analytic in the unit disk, and if I apply this above result, according to the above result, the derivative of this function has to be 1 minus 1z is equal to, it has to be, it was 0, it has to be n greater than or equal to 1, n times z to power n minus 1. So what is the derivative of this 1 upon 1 minus z? You compute it, it comes out to be 1 upon 1 minus z whole square. And this comes out to be equal to n greater than or equal to 1 n z to power n minus 1. And if you want to change the variable, this index n, you replace n by uh, n by n plus 1. You can write this series to be n greater than or equal to 0 to n plus 1 to power z to power. So what it implies? It implies that this function 1 upon 1 minus z whole square can be expressed as a power series. Can be expressed as a power series, or you can say this power series in a red circle. The limit of this power series is nothing but 1 upon 1 minus z whole square. So this is the way you can also use, or the other way you can say that 1 upon 1 minus z whole square, this is an analytic function in the unit disk, and this analytic function is equal to, is a limit function of some power series about a region. So this is the one way. If you differentiate again, you get another function and you get another power series of that function. You keep on differentiating, you get so many power series and the functions corresponding to those power series. So this is a one way of seeing these things, and another that intuition that you must have right now is that this is an analytic function. Look at this thing. What we just obtained, that this is an analytic function z square, and through certain techniques we obtain a power series expansion of this function a n n plus 1. Let me write only a and why I am writing n plus 1. We obtained power series expansion of this function, where the coefficients that a and we obtained are n plus 1. And this is not a particular case of an analytic function. We will, in the next chapter, we will prove such a result for arbitrary analytic function, that if you have an analytic function on any domain, if you have analytic function on any domain, then we will prove that about each point in that domain, let us draw the largest possible disk which do not go outside this domain. Then in that largest possible disk, this f will be, we will be able to write this f as a power series given by, let this be z naught a n z minus z naught to power n. We will be able to write this in this way, where a n's are coefficients. And what are the a n's are the coefficients? You know what are a n's. A n's has to be nth derivative of at z naught upon n factorial. And this is also known as Taylor's series. Taylor's series. It should have been in your unit 2, but anyways, according to syllabus, it has to be in unit 3, and we will cover it there. So, okay, let me move on. Another thing about power series, and another way of finding the power series of some functions, or the limit functions of some power series, can be through integration. Why through integration? Because since if you have a power series, this one, what are the facts about this power series? It has a radius of convergence. So it has a radius of so it has a disk of convergence, and let disk has radius r. Then this power series converges absolutely for every point in this disk of convergence, and for every smaller subdisk, oh, I'm changing the color, I'm getting again the same color. Okay, yeah, for every smaller subdisk inside this disk of convergence, in that part, this power series is uniformly convergent. This is uniformly convergent. And if we take certain contour, inside this smaller subdisk, starting from some point, let it start from 0 to जहां आपके पास power series centered at to some point z. So I can take the line integral of the limit function of this power series, and again on this contour also, this power series has to be uniformly convergent because it is within this subdisk of the disk of convergence. And you very well know that in case of uniform convergence of this series, the summation and integration can be interchanged. So therefore, this thing, I'm writing just 0 to z, means the line integral on the contour which starts from 0 and set z. So it has to be f of, let us say, f of xi something. So it has to be integral 0 to z, use the value, this is a n xi to power n t xi. Now, using the concept of uniform convergence on this contour 0 to z, I can interchange summation and integral, whatever this range of the summation is, I can take it to 0 to z, zeta, xi, n, d, xi. Now you can differentiate it. That means you can differentiate it, integrate it also. The term was, and so what you will get, you integrate this I power n. What you get psi power n plus 1 upon, I have coefficients also, you just keep the coefficient because it's a constant, it has nothing to do with a n upon n plus 1. So here you have this thing, and you have to take the limit from 0 to z, but at 0 it has to be 0, so it has to be z to power n plus 1. So you got another power series. This is another power series, and the limit function of this power series is obtained by integrating the limit function of this original power series. This one is it. This is a Gauss. Also, the another thing that you must to get to know from here is that this power series and this original power series, they have the same radius of convergence, and this can be verified as well. So using this integration part, you have to show this thing. I will leave it as an exercise for you. You have to show this thing that minus principal branch of log 1 minus z is equal to z plus z square. This is the expansion of this log function about 1 3 plus z4 about 4 plus so on. This is for mod z less than 1. And what you just integrate this geometric series and you will get this thing here. Okay, do you have any questions? So, okay, then if you don't have, let's move on. Let me clear these boards because I might require. So the another important thing that we have to prove is a result which is also known as uniqueness theorem. Uniqueness theorem for power series. We will also prove uniqueness theorem for analytic functions, but we will prove it in another unit. But here we are going to prove it for power series. So what is this power series uniqueness? Suppose we have two power series and their limit functions. Suppose we have the power series representing a function fz, and we are going to take the power series about origin as the standard procedure that we have adopted, and another power series representing limit function gz, and suppose these both power series converges for a common disk. Let first power series converges for radius of convergence R1, and the other power series converges for radius of convergence R2 respectively. Obviously, you have two different power series. It's not possible always that they will have the same radius of convergence. They might have different. So this is the hypothesis. Now, if we have this condition, fzk is equal to gzk for a sequence zk of non-zero. Why I'm taking non-zero? Because here the center is 0. If center would have been z naught, we should have taken zk with those points which are different from z naught. Non-zero complex numbers in certain disk. I will tell you what delta is, such that this sequence is convergent sequence, that is converges to the center as k tends to infinity, where delta I am taking to be some positive number, but it has to be less than minimum of R1 and R2. It should not be bigger than both of at least one of them. Then it says that all the coefficients of the power series, corresponding power series, are equal. और सारे कोफिशिएंट्स अगर इक्वल होते हैं तो हैंस आपके पास पूरे के पूरे दोनों फंक्शंस आपस में इक्वल हो जाएंगे. जो भी कॉमन पार्ट आपके पास हो जाएगा, कॉमन वाले पोर्शन पे आपके पास ये दोनों के दोनों फंक्शंस इक्वल हो जाएंगे। कैसे आपके पास ये इस तरीके से हो जाएगा, क्योंकि सेंटर है ना, सेंटर आपके पास रेडियस ऑफ कन्वर ये सॉरी आपके पास जो सेंटर है पावर सीरीज का, दोनों पावर सीरीज का सेंटर कॉमन है, तो ऑब्वियसली इनकी जो डिस्क ऑफ कन्वर्जेंस होंगी वो कॉन्सेंट्रिक डिस्क होंगी जी। दे हैव टू बी कॉन्सेंट्रिक डिस्क। तो दोनों के दोनों पावर सीरीज जो कन्वर्ज करेंगी वो इस कॉमन वाले रीजन पे कन्वर्ज करेंगी। इस पर ये वाला कॉमन वाला रीजन कन्वर्जेंस का होगा। तो so what this hypothesis is telling us is, it is telling us that if you have a sequence within this of some points and this sequence is converging to zero, and such that at each term of this sequence the two functions agree, the two limit functions are same, then it implies that the coefficients of these two power series are same. इन पावर सीरीज के कोफिशिएंट्स भी सेम होंगे। अगर इन पावर सीरीज के कोफिशिएंट सेम हो जाएंगे तो आपके पास जो ये पार्ट आ जाएगा जी। अब देखो ना, यहाँ से सिर्फ बहुत सारी चीजें आप डिड्यूस कर सकते हो। लेट मी मूव ऑन, लेट मी गो टू द नेक्स्ट स्टेज, लेट मी क्लियर दिस वन। आपके पास अगर दो पावर सीरीज आ गई ए एन जेड टू पावर एन और बी एन जेड टू पावर एन, तो once you get this conclusion that once you know that आपके पास कोफिशिएंट्स बराबर आ गए दोनों पावर सीरीज के, तो अगर कोफिशिएंट्स बराबर आ गए तो इसका मतलब आपके पास, क्योंकि रेडियस ऑफ कन्वर्जेंस क्या होता है आपके पास, यू विल हैव दिस थिंग, लिमिट सुपीरियर ऑफ mod a n nth root will be same as limit superior of nth root of mod bn, ये भी इक्वल हो जाएंगे। तो इसका मतलब इनके रेसिप्रोकल्स भी इक्वल हो जाएंगे। इसका मतलब इन दोनों पावर सीरीज के जो रेडियस ऑफ कन्वर्जेंस है वो भी सेम हो जाएंगे। दोनों पावर सीरीज का रेडियस ऑफ कन्वर्जेंस बराबर हो जाएगा और कोफिशिएंट्स इक्वल होंगे। तो आप देखिए कोफिशिएंट्स इक्वल हो जाएंगे तो आल्सो आपके पास ये दोनों की दोनों पावर सीरीज सेम हो जाएंगी। both these power series will be same, both these power series will be same and hence अगर ये सेम हो जाएंगे तो आपके पास फंक्शंस भी इक्वल हो जाएंगे जो आइडेंटिकली जी जेड आपके पास इक्वल हो जाएंगे ऑन द डिस्क ऑफ कन्वर्जेंस, और वेयर आर आई एम टेकिंग द कॉमन वैल्यू ऑफ आर एंड आर वन। तो अल्टीमेटली ये यूनिकनेस है आपके पास कि दोनों फंक्शंस इक्वल आ गए। अब देखो आपके पास हाइपोथेसिस में फंक्शंस पूरे डोमेन पे इक्वल नहीं थे, आपको जस्ट इतना कहा गया था कि आपके पास जो फंक्शंस हैं वो जस्ट कुछ एक सीक्वेंस में, आपके पास ये डिस्क है, इस डिस्क के अंदर एक सीक्वेंस है पॉइंट्स की, बस वो कन्वर्जेंट सीक्वेंस है, उसका लिमिट पॉइंट है उस सीक्वेंस का, इस तरह से सीक्वेंस है, कोई सीक्वेंस है पॉइंट्स की, वो कन्वर्ज कर रही है सेंटर पे, और इस सीक्वेंस के पॉइंट्स पे आपके पास जो फंक्शंस हैं एफ और जी ये इक्वल है, ये कोइंसाइड करते हैं, ये सेम वैल्यूज लेते हैं। तो बस इतने से हाइपोथेसिस की वजह से आपके पास पूरे के पूरे दोनों फंक्शंस सेम हो जाते हैं, दोनों पावर सीरीज सेम हो जाती हैं। तो दैट्स व्हाई द नेम uniqueness. Is it okay?
So
Okay, then let me write its proof. Let's prove this thing. So what we are going to prove, only we are going to prove that the coefficients of these two power series are same. So because of yesterday's theorem, the limit function of a power series is analytic. That means the limit function that is given to us fz and gz are analytic functions, in their respective uh, disks of convergence, जो भी अभी इनकी disk of convergence है, in their respective Let me write in their respective disks of convergence. और अगर एनालिटिक हैं तो कंटिन्यूअस भी होंगे, तो so they are continuous because analytic function is differentiable and differentiable is always continuous function. They are continuous also. Thus now we will make the use of continuity. We have this as a part of hypothesis. So this implies that limit k tends to infinity, f of zk has to be same as limit k tends to infinity gk. But now I'm going to make the use of continuity. According to the continuity, limit k approaches to infinity, f of zk has to be f of limit of zk. What is the limit of zk is 0. And similarly, the limit k to infinity g of zk has to be g of limit of zk. What is the limit of zk is 0. So we get this thing that f of 0 is equal to g of 0. So but what is f of 0? If you see, f of 0 is the coefficient a0 and g of 0 is a coefficient b0. So this implies that the first coefficients, which are a0 and b0 of these two power series, are same. ये अभी एटलीस्ट आपके पास हो गया. So ये हो गया n equal to 0 के लिए. Now we are going to establish other things by using the induction hypothesis, induction method of induction. So to complete the proof, we use the method of induction. We have already for n equal to 0, so we assume the induction hypothesis and we suppose that coefficients aj is equal to bj for j equal to 0, 1, so on up to m minus 1, and we will show that a m is also equal to bm. Then f of zk is equal to g of zk implies, by definition, it has to be n equal to 0 to infinity a n z k to power n is equal to, this is the power series of fz, and for gz it has to be n equal to 0 to infinity bn z to power k to power n. But let me separate things. I'm going to write a naught zk plus so on up to a m minus 1 zk to power m minus 1, okay, plus summation n greater than or equal to m a n zk to power n, and this has to be equal to, राइट हैंड साइड पे भी मैं यही जो कोफिशिएंट्स इक्वल है उनको एक जगह लिख लेता हूँ, तो आपके पास हो जाएगा इट हैज टू बी b नॉट zk plus 1 plus it has to be b m minus 1 zk to power m minus 1 plus n greater than or equal to m b n zk to power n. Now look at this thing. According to our hypothesis, a naught is equal to b naught and so on. A1 will be equal to b1. am minus 1 is equal to bm minus 1. So that means these two polynomial expressions are same. अगर ये same है तो you just cancel out additively. So what you are left with now is that this implies that you will have leftover things is n greater than or equal to m, a n z k to power n is equal to summation b n z k to power n greater than or equal to m. Okay, these two power series are convergent, and now I can multiply this with some number. And what I'm going to multiply it with, I'm going to multiply it with zk to power minus m. So when I multiply it zk to power minus m, because zk is a non-zero quantity, since you know that zk is not equal to 0. So multiplying it with 0 will not change anything. It will not, otherwise multiplying it with 0 would make both the sides 0, and it will not give us anything. So this implies I get this here, uh, n greater than or equal to m, a n, if I multiply it with minus m, I will be having n minus m is equal to summation n bigger than or equal to m p n z k power n minus m. And the reason why it will remain this, because zk is a non-zero quantity. So again, both the right hand and left hand side are power series, and this is a power series, and suppose this power series represents a function f, and if it represents another power series, this right hand side one, suppose it represents a power function g, and then it implies that f at zk is equal to g at zk. Okay, let me write where f of z is the limit function of this power series n greater than or equal to m a n z to power n minus m, and gz is the limit function of this power series n bigger than or equal to m b n z to power n minus n. अब देखिए, एक पावर सीरीज में से कुछ फाइनाइटली मेनी टर्म्स को अगर आप रिमूव करें तो उससे फर्क नहीं पड़ता है, ठीक है? Why? Let me write it this way. Since the radius of convergence of this power series a and z to power n greater than or equal to 0, and summation n bigger than or equal to m a and z to power n minus m is same. They will have the same radius of convergence, क्योंकि radius of convergence के लिए z की powers मैटर नहीं करती हैं, कोफिशिएंट्स मैटर करते हैं. तो पावर सीरीज के जो कोफिशिएंट्स हैं, पहली पावर सीरीज के कोफिशिएंट में ज्यादा कोफिशिएंट्स हैं, m कोफिशिएंट्स ज्यादा हैं, दूसरी में फर्स्ट m कोफिशिएंट्स नहीं है, बट लिमिटिंग के लिए तो बाकी कोफिशिएंट सारे सेम हैं, तो दोनों की लिमिट्स बराबर हो जाएंगी. तो लिमिट्स बराबर हो जाएंगी, लिमिट सुपीरियर आप जो nth रूट करके आप हेडमार्ट फॉर्मूले से रेडियस ऑफ कन्वर्जेंस निकालते हैं, तो वो दोनों का बराबर आ जाएगा. तो दोनों का बराबर आ जाएगा, तो इसका मतलब रेडियस ऑफ कन्वर्जेंस इन दोनों का बराबर, और इसका रेडियस ऑफ कन्वर्जेंस सम r1 है, ठीक है, वो पॉजिटिव रेडियस ऑफ कन्वर्जेंस है. तो दैट मीन्स ये पावर सीरीज का भी एक पॉजिटिव रेडियस ऑफ कन्वर्जेंस है. अगर इसका रेडियस ऑफ कन्वर्जेंस पॉजिटिव है तो दैट मीन्स आपका जो कैपिटल एफ जेड जो इसका लिमिट फंक्शन है वो एनालिटिक होगा डिस्क ऑफ कन्वर्जेंस में. इन पर्टिकुलर आपके पास एनालिटिक है तो इन पर्टिकुलर एफ जेड कंटिन्यूअस होगा, ये कंटिन्यूअस होगा इन दिस डिस्क ऑफ कन्वर्जेंस. और इसी तरह सिमिलरली यही आर्गुमेंट से आपके पास यू कैन से दैट gz is g is I am just not g is continuous g is continuous in its respective disk of convergence. So let's make again the use of continuity since they are continuous. So f of zk being equal to g of zk, ये हमें मिला this will imply that applying limit to both sides will be same. And now use the concept of continuity. What is has to be limit of limit k goes to infinity f of zk has to be f of limit of zk, but limit of zk is f of 0, and it will be equal to limit of k goes to infinity g of zk, but limit of k goes to infinity g of zk has to be g of limit of zk, which is again g of 0. But what is g of 0? Look here. Let me look at this thing. Let me you look at this thing. If you expand this power series, let me expand this one so that you get. If you expand, what is the first term? If you substitute n equals to m, you will have bm and z to power 0. So it will start with bm. Next, it will be bm plus 1 z plus bm plus 2 z square. This power series like this, and similarly here, this is am plus 1 z plus 1. So when you consider g of 0, g of 0 will be b of m, and similarly here f of 0 will be a of m. So that means when you say that f of 0 equal to g of 0 implies that you say that am is equal to bm, and this is what we were supposed to show through induction method, and this completes the induction method and hence the proof. Hence it completes the induction method, and hence we get that an is equal to bn for every n greater than or equal to 0, and this completes the proof of this uniqueness theorem. So if you have any question about this uniqueness theorem, you can ask. बोलिए जी. You don't have any questions?
No, sir.
Okay, then I think this has to be the last topic of this chapter, and besides that, after that we might have some several exercises. But the last thing that we have to talk about is the algebraic operations of power series. But sum and difference being simple, that I don't need to talk about. The sum of power series is again a power series, and what will be the radius of convergence that has to be discussed there. That has to be minimum or the something like that. But let me take a bit non-trivial thing, that is the product of power series. So how we are going to define product of power series? If we have two power series, how we are going to define product of power series? The first thing, that if you want to define the product of the two power series, just take both the power series to be centered about same common. They must have the common center. And you can try, what if the power series do not have a common center? What happens then? And suppose let us take a power series whose limit function is f of z, and without loss of generality I am again taking the power series about origin. And let me take another power series whose limit function is bn zn. Now the question is, and obviously this has to be disk of convergence, and let it be the minimum. Minimum means f the power series representing f will have a different radius of convergence, and the power series representing g will have another radius of convergence. So I'm taking minimum of both the radius of convergence, let it be r, and that means both the power series are convergent. Both the power series are convergent in mod z. I'm not saying that this is the radius of convergence of both the power series, but yeah, both the power series are convergent there. Uh, Now the question is convergent there, and so f and g both are analytic functions in this disk. So you already know that product of analytic function is analytic. That means f dot gz is analytic, and d0 r. Now the question is, okay, if you substitute in place of f this power series, and in place of gz, you substitute its power series p and zn. Now the question is, what is its product? So we need to first define what is the product of the two power series. Then we will actually show that the corresponding power series. Suppose we obtain something like this as a product of these two power series. Then we will have to show that the limit function of this power series is nothing but is actually a product of the limit functions of the corresponding power series. We have to show this thing. But first, let's talk about how we are going to define this product. And this product is also known as Cauchy product. This is also known as Cauchy product. How we could define it? We define if you have two power series and you have another power series, and it will be another power series Cn z to power n, but where Cn's are the coefficients that you need to know, where C naught is a coefficient which is product of A naught and B naught. So you can guess it if you take instead of you taking the polynomial in infinite series, you just take the finite series. Then you multiply, you will get the guesses. Okay, what should be the coefficients? C1 has to be A naught B1 plus A1 B naught. Similarly, C2 will be A naught B2 plus A1 B1 plus A2 B naught, and likewise C, the coefficient Cn will be summation AK Bn minus k, where k runs from 0 to n. And the guess that you can have in your mind is, when you take this summation, you look at the indices of A and B and take the sum of these two indices, and this sum is actually n. So these are the coefficients actually, how this is the way these coefficients are defined. So now let's look at its convergence part, whether this, if we define the product this way, is it convergent also? Yes, it will be convergent. And I'm quoting here a theorem here that you have written, F. Martin's theorem. I'm stating it, quoting here. I'm not stating exactly. F. Martin's theorem. What this theorem states, it states that if you have two infinite series of real numbers, a n, and let me write not a n so that it may not, let me write the series of real numbers xn and another series yn, and if both the series are convergent, and if one of the series is absolutely convergent, one of the series is absolutely convergent, this is a necessary thing, convergent, and the other is just convergent, and the other is convergent. There are weaker versions of this, that sometimes the other series may not be required to be convergent. Its partial, its sequence of partial sums need to be just bounded. That will be something. But anyways, the setting that we require, I can state here, and the other is convergent. Then their Cauchy product, जो Cauchy product मैंने अभी define किया, is convergent. So this is the requirement for the Cauchy product to be convergent. So now, thus, for each z in this disk of convergence of the power series that we considered, and let us assume that this in this disk where both the power series are convergent, and then in this disk both the power series, a n z to power n and b n z to power n are absolutely convergent, यहाँ पर हमें F Merton says that you just need for each z, when I fix z, then this is not a series of functions, then this is a series of numbers I'm talking about. So this is absolutely convergent, and F Merton's lemma says that out of the two, you just need one to be absolutely convergent, and other can be just a convergent. But here we have a much stronger hypothesis that both the series are absolutely convergent. Hence, by Merton's theorem that I just stated above, Merton's theorem, we see that this series, which is the Cauchy product Zn, is convergent. It's absolutely convergent indeed, because we can take it's absolutely convergent. Is absolutely convergent in this disk of convergence. So this thing is settled that this is actually a convergent. That means the product that we define, the Cauchy product of the power series that we defined, is a well-defined thing, and it represents a certain function. So it is absolutely convergent, hence it represents a function, and let that function be capital F of z equals to summation c n z to power n. And since it is a power series, and what we know about power series is a well-known thing, that it is convergent in this, and it implies that the radius of convergence of this Cauchy product has to be, that is, greater than or equal to r. The meaning, because it is convergence here, so radius of convergence is the maximum of such r. So let's not talk about by the way at this time about radius of convergence. Let's just focus on this. So fz is an analytic function. Now our claim is to establish this thing, that this fz is actually the product of f of z dot g of z. So let's look what we have, by the way, at this time. Now we have this is a power series, and you know what are the coefficients. F of 0 has to be C of 0, but according to Cauchy product, what was C of 0? C of 0 was A naught, B naught, and A naught is a coefficient of the power series representing F, and so it has to be F of 0. And similarly, B naught is a first coefficient of the power series representing G, so it has to be G of 0. So at 0 we have equality. Also, the second coefficient, that is f of, that is derivative of f of 0, it has to be c1, but according to the definition of the Cauchy product, c1 is a naught b1 plus a1 b naught. And what is a naught? A naught is f of 0. And what is b1? B1 is first derivative at 0 plus, it is, what is a1? A1 is derivative of f at 0, and b naught is g of 0. By product rule of the differentiation, it has to be f dot g, the derivative of this at 0. So the first डेरिवेटिव भी आपके पास हो गया. सेकेंड डेरिवेटिव या इन जनरल आपके पास अगर आप if you look at kth derivative, if you look at kth derivative of f at 0 upon k factorial, it has to be let me, instead of writing k, let me use n. I'm comfortable with that. N factorial. uh, you know, this is the coefficient of this power series, and but accordingly Cn was what? Cn was this thing. It was k from 0 to n, a k b n minus 1, b n minus k, and let me write this thing. It has to be k equal to 0 to n. What is this ak? Ak has to be the kth derivative of f at 0 upon k factorial, and this has to be another thing, and b has to be g n minus kth factorial upon n minus k factorial, this thing. So now let us look at this sum. This sum is actually, let me rewrite it, it is k from 0 to n. It is kth derivative of f at 0 over k factorial into g n minus kth derivative at 0 upon n minus k factorial. But I'm going to claim that this thing is nothing but this is going to be f dot g nth derivative at 0. So let me tell how I'm going to go. I'm going to get here. Get here is first, you if you open this sum, you take the LCM out. What you have to take, the n factorial out. You will be having adjusting many things, and you will get a formula that is obtained by differentiating this f dot g whole power n factorial upon n factorial. And by the way, f dot g whole power nth derivative, you just use here the well known theorem from calculus, that is Leibniz theorem. Leibniz theorem, it gives you this thing. It gives you k equal to 0 to n, and it says that you have this thing n c k f kth derivative into derivative of n minus k. And what this expands to, it expands to this thing k equal to 0 to n. What is n? This is n factorial upon k factorial into n minus k factorial, and it is fk g to power n minus k. So this is what you get there in this. Look at here, this part. Let me write, color it so that you can look at here. I just claim it to be this thing. So what I did here, I just took out the n factorial. If I take the n factorial out, what I'm going to get, I'm just going to get n factorial in the numerator. And I have already this product k factorial into n minus k factorial. And by Leibniz theorem, I'm going to get this to be the derivative of product f dot g, the nth derivative. And this thing, so now what we obtained till now, we obtained that for each kth derivative, not only nth, let me write again, n For each nth derivative of f at 0, I have this to be equal to f dot g whole power nth derivative at 0, and this is true for every n. क्योंकि नीचे n factorial भी आ रहा था तो n factorial भी I can cancel out. So we have this thing, and so I'm going to use here a lemma, the exhaustive proof of which we will be talking in the subsequent units through uniqueness limit and the Taylor series, and I'm just stating it here for you that if uh, we have two functions, if f and g are analytic functions, if there are two analytic functions in some disk, let me take it to be disk about, let me take z naught, in some disk such that you have this relation of that nth derivative of f at z naught is same as nth derivative of g at z naught for all n greater than or equal to 0, then this implies that the two functions f is z is equal to g of z for all z in this disk. So because of this lemma, in our setting we have capital F to be, let's give capital F to be f, and in our setting capital F, thus capital F of z, and capital G has to be product f of g of z. So it has to be, both the functions have to be equal to f dot gz for all z in the subsequent disk of convergence, and this is what we wanted to show. That's the proof. So this is it. So let me take some questions from you. If you have, please ask. बोलिए जी. I have a question in chat. I have e I x cos x plus I sin x is the example of product of power series. If yes, can you explain how it is an example of product of power series? I'm not getting how it is a product of power series here. It might be, but not explicitly. It is not visible here that e I x is a, it's just an entire function. That's it. It has its power series expansion, but that part we will be discussing in next chapter, that you have an analytic function, you can expand it into the power series. We have